Okay, so we're going to be taking a look at a problem and some variants of it. So if you're a current student, you might recognize this as a recitation question. And yes, I'll go through the solution once again. But when I taught this during recitation, one of my students, I forgot your name, I'm sorry, it was the first recitation, asked an excellent question. And that's a question we're going to explore in this video, and it's going to come to a really, really cool conclusion. If you're a former student, still watch it anyways, because if you enjoy like math and like some beauty, you're going to be really surprised by what we find out in this problem. So yeah, if you're a former student, get your 1600 friends and put it up in like a GSR or whatever and watch this video. This is really cool, and I'm very thankful for the student who asked this question. But before we get into the question that was asked, let's look at this question and solve it. So the question asks, how many 5-digit binary strings are there such that every 0 is immediately followed by a 1? So a binary string is basically a set of characters in a row such that each character is a 1 or a 0. For example, one such binary string could be this. This is a 5-digit binary string. Everything's a 1 or a 0. However, this question is asking, out of all such 5-digit binary strings, how many are there such that every 0 is immediately followed by a 1? So this would not work out. This would be invalid because this first 0 does not have a 1 immediately after it. So an example of a valid string could be something like 10111, because for every 0 there's a 1 immediately after it. Or maybe something like here, where we have 2 zeros, but each 0 has a 1 immediately after it. So to solve this question, a good starting point is like, what is the structure of such a string? Like, we know that each one has to have a 1s or 0s, but we don't necessarily know how many 1s or how many 0s. Here we have an example of a string that's valid with just 1 0, and here's another one with 2 zeros. However, a question is, so you might ask, what is the most amount of zeros in a valid string? Right? It's definitely at least 2, because we have such a string that has 2 zeros. But the question is, could it ever be 3 or more? So let's suppose we did have 3 zeros, and we're trying to construct such a valid string. Well, I know if it has to be a valid string, then every 0 must have a 1 immediately after it. And no matter what, we've already exceeded the 5 characters, right? Because each 0 has a 1 after it. That's 6 total characters. So we can't have 3 zeros. Can we have more than 3 zeros, like 4 or 5? No, for the same reason, because each 0 must be followed by a 1. And in that case, with 4 zeros, it would be at least 8 digits long. With 5 zeros, it would be at least 10. My backpack almost fell off a chair. So yeah, so we know that a valid string will have at most 2 zeros. Yeah, so that could mean it could have 0 zeros, it could have 1 0, or 2 zeros. So in fact, what we can do is consider those 3 cases separately, find the amount of strings that fall into each case, and add them up. Yeah, I think I'll have to erase this, and then we'll get into it. So in the first case, we'll consider the valid strings with 0 zeros and figure out how many such strings there are. By the way, I don't know if it's supposed to be OES or just OS. That's why I don't study English and I study something where spelling doesn't matter. So yeah, we're sticking with OES. Maybe I'll just put a question mark above that E just because I'm not too sure. But okay, so this case is pretty simple. if there are 0 zeros, if there are 0 zeros in our string, and each character is either a 0 or a 1, then all the characters must be 1s. Right? Like, not much else to say here. So that means there is only one such string, namely the string 11111. Right? So case 1 has just one string. So let's do case 2. So our second case is the valid strings with 1 0 in it. Okay, so this is slightly more complex. What we can do is imagine we have like a sequence of 5 spaces that we're going to fill in with 1s and 0s. And we're going to construct a valid such string, but we'll only have 1 0. So this one wouldn't be able to be created by the procedure we'll construct. So, what would be a logical first step? Well, either we're going to place the 0, or we'll place the 1s. Why don't we start by just placing the 0 since there's just one of them? So we'll place the 0, but where can the 0 go? Can it go in this spot? Well, yeah, sure, like why not? This spot? Well, yeah, sure, why not? And same, like, on and on, but wait a second. Could we ever put a 0 in the last spot? No. Why? Because every 0 needs to be immediately followed by a 1. If we were to put a 0 in the last spot, we can't put a 1 after it. So we can never put a 0 there. So we'll place the 0. So we'll place the 0 in one of the first 4 spots. One of these 4 spots. And of course, this can be done in 4 ways. And then in step 2, once we've placed the 0 in step 1, maybe in that slot, we'll just fill in the remaining spots with 1s, because that's the only thing that could go there. And here we're certain that there will always be a 1 following the 0. So we can fill in the remaining spots with 1s. This can be done in one way. So by the multiplication rule, we have 4 strings in case 2, right? And in fact, we could just write them out. So this is 1, that's another, and those are the last 2. So we have 4 strings in this case. So we take a mental snapshot of all of this. The only thing we need to remember is 1 and 4, because that's going to be used in our answer. And our last case to consider is the valid strings with 2 zeros. Remember, we said that every valid string will have at most 2 zeros. We've done 0 zeros and 1 0. Now we just have to handle 2 zeros. So again, why don't we consider like 5 spaces? And again, we might be tempted to just go about placing the zeros and then place the 1s. So, suppose we were to go about placing the zeros, right? We know 0 can't go in the last spot. So we want to place zeros here. So let's write out the procedure. So it's a very vague step 1, and that's kind of intentional, just to play around with what it could mean. So if we were to place both zeros, there are a couple of natural quantities that you would use to describe this first step, a couple of potential candidate quantities. For example, we might say that it is 4 times 3 ways, in that we first choose a spot for the first 0, and then we choose one of the remaining spots for the second 0. The issue with this is that the zeros are indistinguishable. So if I choose a spot for my first 0, and then choose a remaining spot for my second 0, this could be obtained by first choosing this spot for the first 0, and that for the second 0. So that's not right. So maybe instead we say, okay, why don't we just, of the 4 locations, choose 2 of them to put them in? That seems better, right? I might choose the 1st and 3rd location. And now we're in business because I'll never choose the 3rd and 1st location. Combinations, unordered, etc., etc. However, we could choose these 2 spots. And that's not good, because here we have a 0 that is not immediately followed by a 1. Okay, so now what? Well, some of you might just be saying, okay, why don't we just count by hand the amount of ways we can place the zeros, right? Like, if I put a 0 in this first spot, I can't put it here, the second one here, because it'll be next to each other, but I could put it in the 3rd spot. I could also put one in the 1st spot and put one in the 4th spot. Or I can put a 0 in the 2nd spot and in the 4th spot. Those are my only 3 options. Otherwise, I'll have zeros that are next to each other, and that's not good. So here we would say 3 ways. And then step 2, we'll fill in with the 1s. Which can be done in one way. So by multiplication rule, there are 3 valid strings in this case. And so, like, to conclude the problem, we take the sum of the amount of strings in each case, and we would get 1 plus 4 plus 3 equals 8. And there's a couple of things you're probably thinking to yourself. First of all is like, Ishaan, that wasn't that interesting. You promised it was going to be very exciting. We're not there yet. We are just getting started. There's a lot more exciting stuff to come. So I'm going to hold on to that promise and saying that some magic is going to appear and something you're not expecting, unless I spoiled it in the title, which sounds like something I would do. The second thing you're thinking is, 8? Are you kidding me? That's a really boring answer. I could have counted that like on my own. And yeah, you could have. But that lends itself to a pretty good question. And the question is like, okay, what if we weren't looking at 5-digit strings? What if we were looking at like 8-digit strings? So if we had the same question, but we're asking how many 8-digit binary strings are there such that every 0 is immediately followed by a 1, we could follow the same procedure. First, figure out the most amount of zeros that could appear in a string. In this case, it would be 4, because we could have 0, 1, 0, 1, 0, 1, 0, 1. And more than 4 zeros would be like 5 or more. That would be 10 or more digits. That would be no good. So we would say there's at most 4 zeros. And then we could do casework once again. No big deal. It's just a couple more cases. But like, we would still have this case here, the valid strings with exactly 2 zeros. And if we go about doing the same thing as before, where we consider the 8 locations and try to put the zeros, now it's a lot like more annoying. Because before, with the 5 spaces, we could just count by hand and see that there were 3 ways we could put the pair of zeros. Now we could be like, okay, we could put a 0 here and here, and here and here, or here and here, or here and here. And that's going to take like a really long time, right? Like, no one has time for that, right? So maybe there's like a smarter procedure we can follow for this. And in fact, there is. So if we're considering the amount of 8-digit binary strings that are valid, that have exactly 2 zeros, then there's going to be exactly 6 1s. So what we'll do is, let's just pretend we have our 6 1s in a row. Right? We don't know the exact like locations of them within our string. We just know that we will be able to find 6 1s in our string, something like this. All that's missing are the zeros. But we're going to place the zeros a bit strategically here. we know a 1 must be in the last place. That we've already discussed. And we also know that we can't have 2 consecutive zeros. So what if we imagine some spaces in between the ones? Just single spaces. And what if I were to choose 2 such spaces to place my zeros? Right? Maybe I'll squeeze a 0 in between here, and maybe I'll squeeze a 0 in between there, and I just read out whatever I have. 1, 0, 1, 1, 1, 0, 1, 1. Well, hey, that's a valid string. That's length 8, and every 0 is followed immediately by a 1. Does that always work? Let's play the game again. So why don't we number these spaces? 1, 2, 3, 4, 5, 6. And I want you to choose 2 spaces. So yeah, shout it out. Okay, yeah, 1 and 5, right? Yeah, that's a good choice, right? So we could put a 0 here and a 0 here, read that out, and we get 0, 1, 1, 1, 1, 0, 1, 1. And it'll always work. Why? Because we forced zeros to occur immediately before a 1. Like that, we put spaces before every single one, and the spaces are the only places where zeros could be. So by this procedure, we can figure out, we can construct valid strings. So how do we actually quantify this? So just writing it out, we'll consider the 6 spaces that are found 1 before each one, and we're just going to choose 2 of them, and that'll give us the amount of valid strings. Right? So in this case, it would be 6 choose 2. And if we think back to the 5-character strings, for example, just a brief aside, we would have 2 zeros and 3 ones. So we would consider the 3 ones in a line, the 3 spaces, choose 2 of them, and we get the same answer as before, 3. Okay, so this is pretty nifty, right? This is pretty clean. Let's make this a little bit more exciting. So now let's make it real abstract. We're considering n-digit binary strings, and we'll still be under the assumption that we're doing this sort of casework, and we're considering the case where there's k zeros, where k is any sort of valid integer that we could substitute in there. And the logic for this is going to be very much the same as what we just did, right? If there are k zeros, then there's going to be n minus k ones. Right? And again, we'll line up the ones. Of which there are n minus k of them. And consider all of the spaces. So we have n minus k spaces. We just need to choose k of them to place the zeros in. Which can be done in n minus k choose k ways. So this is actually really nice. And okay, so I teased at the start that one of my students asked an excellent question. So the question he asked was when I presented the solution with the 5 digits, and I showed you could choose the spaces in between them. And he asked, is there a closed form solution for this question in particular? How many n-digit binary strings are there such that blah, blah, blah? Is there a closed form answer? Excellent question, right? And immediately in my mind, I was like, well, I don't know. My first thought was to use some sort of thing like this. Why did I show you this? This answer works for any valid value of k, right? If I wanted to figure out the amount of n-digit binary strings with blah, 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 and I'm counting how many valid strings are there with 3 zeros, I just shove 3 in for k down here and put whatever value of n I have there. That'll give me the amount of ways. So this is like for a general case. And so all we need to do is use this for every single case and take the sum altogether, right? So if we sum on all valid values of k, let's write that. Valid k, and take this sum, then we're chilling, right? Like that's our answer. And I'll show you that gets our answer because we just solved the answer for when n equals 5. But first we need to figure out what are valid values of k. So remember, k is describing the amount of zeros we could have in our valid string. So the lower bound for k is clearly 0. Right? We could always have just 0, just 0 zeros. Okay, what about the upper bound? This is where things get a little bit tricky. For 8 digits, we said we could have at least, or at most 4 zeros. And the maximum being 4 was when we had 0, 1, 0, 1, 0, 1, 0, 1. When we had 5 digits, we said at most 2 zeros, because if we had 3 zeros, then each one has to be followed by a 1. That's already at least 6 characters. So it's almost like the maximum amount is half of the total amount of digits. Right? With 8, we would get 4 zeros as our maximum. With 5, half doesn't really work. So we need to experiment with some floors and ceilings. And you can start to play around with other quantities. Like if we were to let n equal 10 digits, well, we could have at least, or at most 5 zeros. And again, the argument is just the alternating 0 and 0, 1, but that doesn't apply for odd. Well, what we can do is just take the amount of digits, divide it by 2, and so that works for even values, but for odd values like 5, it would give 2. We'll just take the floor. So our upper bound for k is the floor of n over 2. So this is like the generic form of our answer. But wait. This is not closed form. I did not answer my student's question. This is what I had in mind, and the entire time I was thinking, how can we do some magic to make this in closed form? Well, I'm about to show you. And this is really, really cool. First, let me confirm that this answer is indeed correct. So this is our formula, and we solved that when n equals 5, our answer is equal to 8. So let's just plug in n equals 5 and see what we get. So this becomes the sum from k equals 0. 5 over 2 is 2.5. Take the floor of that, and we get an upper bound of 2. Of n minus k, choose k, but I'll just put in a 5 in for n. So this is a summation on 3 terms, so let's just write out those 3 terms. So the first is when k equals 0, then when k equals 1, and then when k equals 2. So this is 5 choose 0, plus 4 choose 1, plus 3 choose 2. I forgot the plus sign in there, but you get the point. 5 choose 0 is 1. 4 choose 1 is 4. 3 choose 2 is 3. We get 8. And so not only did we get the correct answer, but if you remember our casework from the very start, case 1, where we had 0 zeros, there was 1 valid string. Case 2, where we had 1 0, there were 4 valid strings, and then there were 3. So this should prove to you that the formula is at least correct. So how do we get a closed form expression from here? And perhaps you're thinking, oh boy, we're going to have to do some sort of crazy math. And maybe you will. But let's experiment with it a little bit. So let's just figure out what our answer is for a bunch of different values of n. Just to have fun with our formula. So for n equals 5, we already said that this was 8. For n equals 1, well, let's not even look at the formula. Let's just try to figure it out ourselves. How many one-digit binary strings are there such that every 0 is immediately followed by a 1? Well, there's only 2 possible binary strings of length 1, 0 or 1. This one's bad because it doesn't have a 1 after it. That one's good, right? So the answer should be 1. And we can verify it with our formula. Boom, there you go, verified, right? Just plug in 1 for n, so the upper bound becomes 0. We change the n to a 1 there. We get just one term because k is going from 0 to 0, and that equals 1. Cool, so that checks out. All right, let's try it again. Right, let's try for n equals 2. And again, there's only 4 such binary strings, right? So we can do this by hand. So here, every 0 is not immediately followed by a 1. Here it is, so that's fine. Here, no, because there needs to be a 1 after this 0. And here, that's fine, right? So the answer should be 2. And let's verify it. And there it is verified, right? Substitute 2 for n, do all of the math, we get 1 plus 1, which is equal to 2. Now, normally this is where you would expect me to say, oh, I'll spare you the time and I'll calculate all of these for you. No, we're actually going to calculate them together. But I'll fast forward it and then we'll just look at the values every time we compute it. But now we'll just use the formula. So next we'll do n equals 3. So here we go for n equals 3. Just verify your work. If you're playing along, we should get 3 as our answer. I wrote this kind of bad. This 5 that's the 8. So here we go. We have values for when n equals 4. That's the math. We get 5. And when n equals 6, we do the math, and we get 13. So let's fill those values in here. So what was the point of all of that? Let's take a look at our answers. 1, 2, 3, 5, 8, 13. Do those numbers look familiar? Hopefully you're saying yes. And if you're not, don't worry, it's like totally fine. These are the Fibonacci numbers. And the Fibonacci numbers are obtained by taking the sum of the prior 2 terms of the Fibonacci sequence. 1 plus 2 equals 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. You better bet that when n equals 7, our answer is going to be 21. Unbelievable. No way this is real, right? I'm just pulling your leg, right? There's no way that the Fibonacci numbers appear in here. But they do. And this is the magic that I was talking about. How come our answer to this seemingly random question about binary strings, why is it the Fibonacci numbers? That's crazy. Here's why. Let's look into it. So this is a modified quasi-definition of the Fibonacci numbers. You'll see that the real Fibonacci numbers have different base cases and maybe different subscripts, but the idea in principle is identical, that each successive term is found by taking the sum of the prior two terms. So, why is this true? Why is this true? This is unbelievable. And the answer is surprisingly simple. Let's consider we were trying to construct an n-digit binary string with that condition there. Well, we've explored different ways of constructing the string, but all of them were like too focused on the digits, like first putting the zeros and then putting the ones. What if we instead put our attention on the locations themselves? That is, I focus in on this first position right here. And we literally have two cases. Case one. The first case is that the first digit is a 1, right? And case 2 will be that the first digit is a 0, but I'm not going to write that out just yet. Okay, so I've put a 1 there. Hooray, good for me. Now I have to fill in the remaining n-1 spaces. But I don't want to do that, because that will take a really long time, and I have to abide by this constraint that every 0 is followed by a 1. But if we were to look at this chunk in its entirety here, this is n-1 spaces. So what kind of things do we have to do within these n-1 spaces? Like, what do we need to do to fill out these spaces such that overall the n spaces is still a valid string? Well, we just need to make sure that, well, since we didn't put a 0 in the first space, whatever 0 we put in any of these spaces needs to be immediately followed by a 1. Well, wait a second. That's just the amount of valid strings of length n-1, right? Because a valid string will have a 0 immediately followed by a 1. So we'll just... So we're just going to fill in this space, these spaces, with a valid n-1 string, n-1 length string, right? No matter what I choose in these spaces, as long as it's valid, the overall string will still be valid. Because once I have a 1 here, it doesn't matter what comes after that. I just need to make sure every 0 in this area is followed by a 1. So in this case, if we're saying like f subscript whatever is the amount of valid strings, there's going to be f sub n-1 strings here. Now we do case 2. I realize I may have been writing off of the screen, but at this point, it doesn't matter, and hopefully when I'm editing it, I can make things work. But okay, let's take a look at case 2. I won't write anything below it. I'll just kind of explain it out here. So we put a 0 there. Great. Again, we need to fill in the remaining n-1 spaces. But now we have to be concerned about this space in particular, right? That has to be a 1. So it can't just be all valid n-1 length strings, because some of them might start with a 0. So how can we reconcile that? Well, let's just shove a 1 there, right? A 1 has to go in that second position. So now let's block this off as its own entity and consider the remaining n-2 spaces. And again, we're left with the same situation. It doesn't matter what I put in here. As long as every 0 is immediately followed by a 1, I'm fine. And how many such strings could fill in these n-2 spaces? F sub n-2. So by the addition rule, we get that. And that's it. That's it. Somehow our ugly formula from before, that was still extremely creative, how we got that answer. Somehow, it's the Fibonacci numbers. And that's it. It's pretty beautiful that in a random question, the Fibonacci numbers just appear. So first of all, to the student in my recitation who asked me, what is the closed form solution, there you go. I mean, hopefully that's cool. But second of all, like, thank you so much. Like, it was really, really cool to find this and like figure out like the explanation of why it's the Fibonacci numbers. And you know, to whomever is watching it, I hope you enjoyed the magic of it as well. And this is where math is really cool, where we just see things we don't expect. Yeah, I'm just happy I got the chance to share this with you. Again, thank you to that student. I'm so sorry I can't remember your name right now. And I don't want to miscredit you, but a lot of credit to you for making me think of all of this. So, yep, that's it. Good. Yes, thank you. Have a good one. Take care.